Hi, everyone. Thank you for joining us for our third session of our weekly Wrangling RAG workshops, Multimodal RAG. My name's Anna. I'm an event planner for Reactor, joining you from Redmond, Washington. Before we start, I do have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional, and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenter to answer live. This session is being recorded. It'll be available to view on demand within 24 to 48 hours. With that, I'd love to turn it over to our presenter. Thank you.
Hello, everyone. I hope you guys are all doing well today. Great. Oh, I was just going to say, yes, pull this up. So today we're going to be talking about multimodal RAG, and we're going to be talking about basically all the ways that you can do multimodal RAG. And we're going to start with a little bit of a background, a little bit of a covering of what we've done so far. And then we are going to get into the new stuff. So, I just covered the slide. So first, let's talk a little bit about RAG. If you have been kind of like playing around in the AI space, in the generative AI space for the last year or so, you have probably seen this word thrown around. So RAG is retrieval augmented generation. And basically what it is it's a way to give your LLM access to your data, right? So LLMs are these things that are these models, and they're trained on some amount of data, but none of that data is data like specific to what you're working on. So RAG is just a way to give your data to the LLM. And a RAG application typically consists of a few different pieces. The tech stack looks like this. There's going to be an LLM, which is, of course, the core engine that powers the retrieval augmented generation. It's the generative AI. There's going to be a vector search engine, which is what people typically call a vector database. And what this does is this searches through vectors, which are numeric representations of your data. There's going to be an embedding model. The embedding model takes your data and turns it into embeddings or vectors. And there's going to be some set of frameworks. Usually the frameworks are optional, but it's good to have frameworks that makes your development easier. So that you can use frameworks like orchestration frameworks or quality tuning frameworks or observability frameworks, things like that. So, this is what a RAG application looks like. So there's on the bottom, you see the process of putting your data into the RAG app. And then on the top, you see the process of using it. So what we do is we take some sort of data and we embed that data with an embedding model. And we use that embeddings and we put them into the vector database. And that's the setup. That's the setup for your RAG app. And then on the top, you'll see what happens when you actually use it is you have some sort of query and you ask the LLM something. And then what happens is the LLM takes your query, tries to figure out what you're asking, sends that to the embedding model, gets that embedding, and that embedding model once again sends that embedding to the vector database, which returns to the LLM some of the top results for that embedding. And then the LLM takes those results. It's not always going to be the top one result. It's usually, you can specify this when you create the vector database, but it'll be like 3 or 5 or 10 or whatever. So it takes some results and it turns it to the LLM, and the LLM takes those results, kind of use them as context, puts them together, and sends it back to you. Oh, hey, hello from Seattle. I'm also in Seattle. And then outside of the whole thing, there is I've wrapped it in like a framework for evals. So when you start putting things into production, you're going to want to know what's going on, how they're working, how things like what LLM calls are being made, what embedding calls are being made, what's being passed, all these different things. And you can monitor all this stuff with an evaluation framework. So let's go through some quick history or some quick background knowledge of what all these pieces are, right? So LLMs are generative models, and basically they have GPT, at least the most popular LLM, and today we're going to be using GPT 4.0. GPT is this decoder only type architecture, which was part of a transformer model, which is like an encoder and a decoder, which solves this ability of or solves the problem of context, which is like if you have a long sequence of tokens, if you have a lot of things, then you're going to need a lot of input and output for the right context. And so that's kind of the main reason why these things were made in the first place. And now decoder architectures are the popular architectures for LLMs like GPT. And essentially what it does is it takes some sort of input, some sort of set of tokens as input, and then it uses this thing called an attention matrix. And then it does some fancy math and it produces output that is the most statistically likely output for it to produce. And then when you're working with vectors, the main thing you're doing is vector search. So vector search is comparing these vectors and seeing how close they are. What you would do, there's many different ways to do vector search, but the idea behind it is that two vectors that mean very similar things are going to be closer than two vectors that mean dissimilar things. So in this example at the top, you can see that puppy and dog are very close. And then next to them is cat. Cat is pretty close to dog, and it's a little bit further from puppy than dog, but it's still pretty close to puppy. And then we see houses, which, although, a lot of people have puppies, dogs, cats, whatever in their house, puppies, dogs, and cats don't have much to do with houses. And so houses is further away from puppy, dogs, and cats than they are from each other. So basically the idea here is you're just taking a bunch of numbers, you're doing some math, and you're trying to find some distances. Embedding models are the models that we use to take our data, our unstructured data, and turn it into these vector embeddings. So this example image here is of text, but today we're going to be working with a embedding model that can do both text and images, as we are working on multimodal RAG today. And the workshop for this specific tech stack, the tech stack for this specific workshop is going to be OpenAI for our LLM. So we're going to be using GPT 4.0. We're going to be using Face, which is Facebook AI similarity search for our vector search. We're going to be using Clip, OpenClip specifically for our embeddings. We're going to be using LangChain as our orchestration framework. And we're going to be using Arise Phoenix for our evals, our tracing, and stuff like that. So basically, the workshop architecture looks something like this. We're going to take our data. We're going to put it into a clip, which we're going to get from Hugging Face. And we're going to put that into Face, which is going to be our vector database. And the embedding LLM vector database triad is going to be encapsulated in LangChain. Really, like putting the data in and your querying is also going to be inside the LangChain framework, but really LangChain helps you orchestrate these three things. So this is what our workshop architecture is going to look like. On the outside, everything is being evaluated by Phoenix. So what makes something multimodal? There's a bunch of different definitions, and if you've been looking at AI stuff, you've probably seen the word multimodal used in a bunch of different contexts. And what it really means is we're just going to be working with multiple types of data. And that could mean that you're working with text and audio, text and images, audio, video, blah, blah, blah. Like all of these different types of data can count as multimodal data. However, in this example, what we're going to be talking about is we're going to be talking about images and text. And we're going to be working with this model called ClipVit. So CLIP is something it says for contrastive language image. I totally forgot what CLIP stands for. But basically what it does is it allows you to embed images and text. And the main thing that is, let's say, difficult about working with multimodal data is that vectors still need to be compared. And the only way that you can quantitatively compare vectors is if these vectors are the same length. So if you have vectors of different lengths, you can't compare them. And that's one of the challenges of working with multimodal data is different types of embedding models are meant to embed different kinds of data. And different kinds of embedding models have different dimensionalities or lengths, because the length slash dimensionality of an embedding model is you get that from the second to last layer of the model. Oh, CLIP stands for contrastive language image pre-training. Thank you, Anna. Yes, so basically the way that you can do multimodal data with images and text is that you have to have a model that can embed both of these using the same dimensions. Okay, so this is also a good time to pause for questions. If you have questions about anything I just talked about, drop them in the chat and let me know. Whoops. So the concepts that we're going to be covering today that from the workshop, like the live session that we haven't talked about before, include tracing. Actually, I think we talked about tracing last time in the Improving RAG one. But it's good to know what tracing is. So tracing is basically like knowing how or where the LLM calls are coming from. And then one of the important things is we're going to be using base 64 for our images. So the way that we interpret our images, the way that the LLM interprets our images is by taking it and turning it into a base 64 string. So it's still kind of like language in a way, but it's like text. It's text. We're gonna turn it into some sort of text, and then it's gonna be able to parse that as an image. And then I already covered this, but multimodality just really means multiple data types, images, text, videos, all these sorts of things. Other ways that people will mention multimodal data that you may hear that is not really pertinent to what we're talking about today would be like multiple vectors. So maybe you have multiple embedding models, or you have different types of embeddings. You could have sparse embeddings, like binary embeddings. Like if you've worked in natural language processing for a while, you've probably heard the term TF-IDF, which is term frequency inverse document frequency, which is one way to compare text documents. Or you could have embeddings from different embedding models. But multiple vectors is usually used for like something like re-ranking. So you would pull some vectors, you would get like maybe like the top 10 results from your vector database, and then you would use another set of vectors to compare those vectors to some other version of your input data, and then you would re-rank those the subset of vectors. So that's one way that some people may say multimodal. I think that's kind of going out of fashion. It's not really something that's covered a lot. Like I was saying earlier, like video, audio, PDF, tables, CSVs even, really different ways, different data types. And then the other thing is like we might be thinking about like different ways to search data. I kind of mentioned this before with like the sparse vectors and stuff like that. But these are all things that can count as multimodal. So let's see. Okay, if there's any questions about any of this stuff, feel free to drop any questions in the comments and I will address them. Meanwhile, meanwhile, I'm going to pull up the code. Let's see, where is it? Okay. Okay, one sec. I'll be right back. Okay. If I sound stuffy, it's because I am stuffy right now. I went on a trip last week and hopefully I didn't get too sick, but my nose is kind of stuffy. So anyway, we're gonna get into I don't see any like questions about the concept, so we're gonna just get into how to build this stuff. So first, like the first thing that you probably need to know about this is um, multimodal stuff is really new and it's really finicky, and so I would like be careful with trying to set this up. You're probably going to run into a lot of versioning errors, so make sure that you use a virtual environment that is freshly installed and is like, totally clean. So um, also, it doesn't a lot of these libraries don't tend to work well with like Python 3.12. So I'm using 3.10. I think 3.11 might be okay, but I'm using 3.10 just to be safe. So the first thing I'm doing here is I'm getting setup tools. I'm using a specific version of setup tools. So if you use Python a lot, you'll probably know that we're on setup tools 70 something now. But I'm going all the way back to 69, 69.5.1. And this is because of all of the other libraries that I'm using, including NumPy 1.21. So you'll also, if you do a lot of data science, you'll know we're on NumPy like 2 point something now. But we're going back to NumPy 1.2.21.3 for this. And then we're also getting Torch and Torch Vision, which I did not specify for this because they seem to be compatible. So these are the PyTorch and PyTorch Vision modules, right? Like these are the neural network training modules. And then FTFY is basically for supporting these modules. And then we're also going back to face 1.7. I believe we're on face 1.8, maybe face 2 point something now. But we have to go back to 1.7 because of compatibility issues. OpenClip, so that's OpenAI's clip model. LangChain community, LangChain experimental. So LangChain experimental is the way that we are able to get the clip embeddings, which is really interesting because LangChain experimental is like your newest, most updated experimental version of LangChain, and then it's like we actually have to go back a few versions to work with the right versions of NumPy and stuff to get things to work. And the last two I have here, or the last three, I guess, are LangChain OpenAI. So this is how we use OpenAI. This is how we use GPT-4o. And then OpenClip Torch. So basically, this is how you get Clip to work with PyTorch. And then we're going to be using Arise Phoenix for our evals, as I mentioned earlier. So let's take a look at some of these images that I have here. We've got this cute cat, this other cute cat, some more cute cats. This one's very adorable, very yowling cat. This dog, this other cute dog. Basically, we have a bunch of cute pictures of pets. And oh, is there a way we can get the code later? Yes, actually, let me just like put the GitHub for this. Okay, Anna, there's the link to the GitHub. Okay, where'd it go? Here it is. Okay, so that's the images that we're going to be using. And the first thing we're doing here is we're just setting up some setup stuff, right? So we're in documents because we're going to have to create some documents in LangChain. And then we're just going to glob these paths together. So glob is just a library that lets you put these paths together. So we're going to get all of the JPEG images. They may be PNG, they may be whatever, that you can use whatever images you want. We're just using these JPEG images. And then I'm going to import face from the vector stores. And then here, we're just doing some more setup. All I'm doing here is getting my OpenAI API key and loading up my environment variables. So this is my preferred way of handling environment variables. If you have other ways to work with environment variables, feel free to work with them however you would like. Oh yes, I think let me start this. I hope things work. Okay. So now what I'm doing here is I'm just launching the Phoenix app. So later on, we'll take a look at tracing later. This is basically just, hey, what's being fed into the LLM. So this is how we have Phoenix working. We're using the LangChain instrumenter. So LangChain and Phoenix, basically, this is the way that you can get Phoenix to work with LangChain. Here you'll see we're getting the open clip embeddings, and then base 64, which is how we're going to be encoding these. Okay. So earlier, I talked about this. We're going to be using base 64 strings, basically. So I've got this empty list here called LangChain docs, LC docs, which is going to turn our images into documents to put into LangChain. And the first thing we're going to do here is we're going to open this. We're going to make this function. So this is a function that does something. We're not actually going to do anything here. So this function just takes in the path, one of these paths that we made earlier. And it's going to open that image file and read it in as a set of bytes. And then we're going to take that and we're going to use base 64 to get the encoding of that, and then use the UTF-8 decoding of that into a string. Okay, so this will return some sort of string. And now we're going to go and we're going to loop through all of those paths, and we're going to create a page content to look up strings just to help us look things up if we need to. This is like not a metadata filtering. Or I think, no, actually, I think this path, this is, no, there it is. Okay. So this is one way to store metadata. This is how you explicitly store metadata. And then we basically say, like, here is where we're finding our image. And so later on, when we find this image, we can like pull back the actual image. And this is just lookup index. Okay. And then once we create this document, we're just going to append it to our empty list. Did I run this yet? No, I didn't. Okay. Okay. And now what we're going to do is we're going to take these documents and we're going to feed them to the vector store using the OpenClip embeddings. So what we're doing here is we're taking these images and we're like embedding all of these images, and then we're storing those embeddings into the vector store. This will take a while. I guess it'll take like 30 seconds to a minute, hopefully. Oh, that was fast. Okay, 22 seconds. Sometimes this takes a little while longer, but good for us. So all we're doing here is turning this vector store into a retriever. So once you have the data stored into a vector store, you're going to be able to want to retrieve that data. And so using the as retriever function, this is just LangChain's way of taking that vector store and putting a retriever function on top of it. And so what it does is it basically says like, hey, like you can just give us a string. You don't have to give us the embedding, right? So earlier when we talked about how RAG worked, we talked about how you have to take the text, you have to embed it, and then it goes to the vector database to retrieve stuff. But in this case, by setting it up as a retriever, what we can do is we can abstract out that embedding step for us. So then all we have to do is give it the text, and it will retrieve it for us. Okay, so again, now we're going to be dealing with basically like how we're going to be working with these images and strings. So this is mainly for working with the base64 images. So if an image is encoded as a base64 string, we'll resize it into this size. This is mainly for when we're working on it later. We're going to be calling this to get a list of images. Okay, so basically what we're doing here is we just the base64 string that we just encoded. We're going to decode it, and then we're going to get the image. We're going to get the image. So this is using PIL pillow. This is a very common image library. We're going to get that image. We're going to resize the image, and then we're going to save it as a set of bytes. And we're going to save it as a set of bytes, and then we're going to re-encode the image. So what we did here is we just took the text, turned it into an image, resized the image, turned that resized image into a series of bytes, and then turn that series of bytes into a string. Okay, so that's what this function does. Basically, what it does is it takes one string, converts it into another string that just represents something else. This just checks to make sure that we're working with a base64 string, encoded string. So if we're working with regular text, this is not needed. What this does here is we're going to be taking an empty list of images and empty list of text, and we're going to go through all the documents. Earlier, we created this set of like 10 documents, right? And basically, we're going to like ensure that we have an image. And once we have the image, we're going to append the image resized as some size, whatever we want. So in this case, 250, 250. And then we're going to just take that image and we're going to append that here. So that's what this function does. So now we've taken our set of documents, which were a bunch of images, and we've turned them into a bunch of images of the same size. Okay. Now we're going to be doing the LangChain pipeline stuff. Basically, we're going to be building a LangChain pipeline. So the first thing we're going to do here is we're basically going to say like, okay, we're going to have some way to put the text and context together. Messages, right? So when we're working with LLMs, we need to be able to send some messages to the LLM. And in this case, we've got this empty list for our messages. And then what we're going to do is we're going to take these images, and we're going to send the image to the LLM. We're going to tell it that it's a base64 image. And we're going to say, here's the context, here's the images, here's like, basically it's the first entry. There's only one entry, but it has to be formatted as a list. We're going to take this image and we're going to turn that into a message. So we can keep that as a message in our, like when we're working with the LLM, we need a message there. And then we're going to add the text message. So we're going to say like, we're going to basically give it a prompt, right? So we showed a bunch of pictures of cats and dogs. As an animal lover, Your task is to analyze and interpret images of cute animals, which is a really great job. Please use your extensive knowledge and analytical skills to provide a summary that includes a detailed description of the visual elements of the image, and then we provide some keywords, and basically this is context, so this is the question, and if we have any text or other tables to pass, we pass them here. And then we append it into our messages section, and this is basically we're saying like this is what the human is saying. So you can pass images or text into this. And then what we're going to do is we're going to get our foundational model, or typically we call this an LLM, but since we are doing multimodal data and we're working with images, it's more appropriate to call this a foundational model. We're just going to use OpenAI, and we're going to get GPT-4o Mini. So last month when I did this, I used a different model, and a few days ago when I was running this library, when I was running this code, I was like, oh, okay, like this should work as intended. And guess what? The model that I used last month has already been deprecated, so I had to change up the model to get this to work. And then once we have all of this set up, what we'll do is we will create our LangChain chain, right? This is what LangChain is known for, in which we'll get the context and the question, and then we'll send the prompt function, and we'll send that to the LLM, or the foundational model, and then the foundational model's output, we'll send it to a string parser, and then we'll invoke a German Shepherd. So I believe this is dog image number 1. So we'll say I'm looking for a German Shepherd, and it should return this image here. This is taking. I broke something here. Okay. I broke something, but it still works, I guess. The image features a German Shepherd, breed known for its intelligence and versatility. Here's a detailed description of the visual elements, description of the German Shepherd, coloration. The dog has a classic coat pattern, predominantly black and tan. Really long string here that I'm not going to read all of. And then if I invoke German Shepherd, we see that we get dog 1. And we also see that ironically, or ironically, I don't know if that's the right word, like strangely, we get cats like 5, 4, and 3. So for some reason, these images tend to encode similarly to a German Shepherd. I don't really know why. That's like a data problem. So that's like one of those things where it's like, okay, the data shows that these vectorized images look like the German Shepherd. Don't know why. Cat laying on a white background. So let's look for a cat laying on a white background. Yes, okay. I don't really know why I have more errors, but I have more errors. And it just says, the image features a cat lying down on a soft, light-colored surface, likely a carpet. Here's a detailed description of the visual elements. The main focus is a domestic cat characterized by striking green eyes and a mix of gray and brown fur with distinct tabby stripes. Blah, 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 blah. Okay. And then we search for the cat, and we see images cat 4, which is a cat on like a beige background. I really think this one probably fits better, but I don't know. It doesn't go. Let's do one more search. And actually, this is an interesting one because you'll see this search is going to be wrong. Cat 4 is this cat again, and it's definitely not showing teeth with an open mouth. It should be cat 5, which is on here, but it is the third most similar one. And for some reason, dog 1, the German Shepherd, and dog 4, the cute golden retriever, are up here. But what happens when we call the chain? So this was the vector database. When we try to retrieve it from the vector database, what happens when we call the chain? Image features domestic cat lying on a soft light colored carpet. So it tells us what it is. And so it knows that it's not a cat. Like the LLM knows that it's not a cat with its teeth open. But unfortunately, the vector embeddings in the vector database are not. So someone asked, would changing the embedding model resolve the issue? Yes. So that's like you can see from the vector database and the retrievers that the reason why you're getting like a weird image in response is because of the vectors and the vector store. So the first thing I would look at is looking at changing the embedding model, and or I guess training an embedding model on like a data set that might be like, particular to cats and dogs. So part of it is like OpenClip is like a generalized embedding model, right? It's not an embedding model that's specifically trained on these kinds of animals. And in fact, I'm actually not entirely sure that animals are like a huge part of that data set. It is like, if you really want to, you could probably go online and find like data sets somewhere. I don't think it's like proprietary. At least I'm not entirely sure. But yes, changing the embedding model, changing the data set with what you train it with, like that would help. The final thing that I want to, oh yes, also I'll pause here for any questions. I guess any other questions. But the final thing that we're going to look at here is the tracing. So I think I was getting the errors from the tracing. Aha, here it is. Okay. So basically, this is this is Phoenix, and this will basically go through these chains where it says like, oh, like here's what's being passed through, here's what's being called, and here's like the context. You can see that the image is base 64 encoded, and it looks like this. Very, very very, very long string, basically. And you'll see like, oh, like here's like some details, here's what's going on, like here's the actual input, and here's how we're going to turn it into a string. Like that's what the string output parser does. And you'll see this like, oops, with multiple strings, right? We can see the retriever, the chain, the cat laying down on a white background. Once again, like huge set of strings, stuff like that. So when you work in production, you'll probably need to use this tracing and analyzing more. But for this example, we're just building a proof of concept. We're building a very simple application. What are best practices for embedding models that you can summarize? I would say like there's kinds of like there's a couple ways to kind of like go about this, I guess. So one is like you can train your own embedding models. You can fine tune existing embedding models. These are like the two ways you can kind of go about this. Training your own embedding models, make sure you have really good data, of course. Fine tuning embedding models, once again, make sure you have really good data. But training is going to be harder because you're going to need probably a larger data set. Embedding, so what you can do is you can start with like a generalized model, and then like fine tune it by giving it very specific sets of images that you want to train on. So maybe the example that I give for this often is like with cars, you have like, we're going to take 4 words here. So Ferrari, Bronco, Mustang, pony, horse, whatever. You know that the Ferrari and the pony are horses. Or sorry. You know the Ferrari is a car and the pony is a horse / an animal. But Mustang and Bronco could be a car or a horse / animal. So that's kind of ambiguous. And so with images, I guess it wouldn't be as hard to tell, but with like just text and stuff like that, like you can think about that as like your starting point for embeddings. With these ambiguous embeddings, you may not get the right answer, right? So with images, you as a human, you can say like, of course, this is a car. But like, like if it's a Bronco car, it might be embedded in a similar space to the animal, like Bronco. and in which case you'll have trouble kind of differentiating these, and the model will have trouble differentiating these. And so to fix that error, what you would need to do is you would fine tune embedding models so that, let's say you specifically want to look at cars, you would give it tons of images of cars labeled as Broncos and Mustangs so that it is much more likely to learn that association. Cool. Um, if there's no other questions, I'm happy to wrap this here.
Awesome. Thanks, Eugen, and thanks everybody for joining us. We're always looking to improve our sessions and your experience. If you have any feedback for us, we'd love to hear what you have to say. You can find the link on the screen or in the chat. Today, our event code is 22960. We'll see you on the next one.